So welcome to our another video on the stellar dynamics, and this is the second part of the equation of transfer. So in the first part we have discussed about the basic notations of the absorptions and scattering coefficients, what is the phase function, what is the isotropic radiations and all that stuff. So in this particular video I'm going to derive the differential equation for the equation of transfer in a very simple scenario. So now let's start our video, and first of all we have to quick recap that what we have studied. So let's suppose we have a radiation. So if something is emitting radiation, how we are going to define that in the mathematical term? So the radiation emitted by a volume of element or mass element is defined as EV is equals to the J, here V is a subscript, means frequency, dm dt, and this is d omega, which is a solid angle, and this is dV. So this is how it's defined, and this is called the radiation emitted by a certain mass element dm. And here we can see that from the basic calculus rule that dm can be written as rho d sigma ds. So this is how we are going to define our dm element. So remember, this is a very first equation and very important equation which will be used in the derivation of the differential equation of transfer. It defines the radiation emitted by a small mass element, because you know that when radiation is going inside a certain element, there is a scattering of radiation. There is a different type of phenomena like the absorption of radiation, the emitter of radiation, that's all going in there. So this is our first definition of the radiation emitted by a small mass element. So remember this particular formula, we are going to use this particular formula in our derivation very much. So this is our first term which we have encountered. This is our term, and let's write about that what exactly here is this particular term. So this JV is the coefficient which is making this particular quantity as equal to sign, because this our energy is directly proportional to dm dt, the solid angle, and dv, which is the frequency. D mu is a very good term to understand this. So this is d mu. So our energy is directly proportional to this, and jv you can see that is a coefficient, a constant that came to hold the equality sign. So this j subscript mu is generally defined as the energy emitted per unit mass, per unit time, per unit solid angle in a unit frequency. So this is how this particular quantity is defined, and you can find this by seeing that in this particular equation, if you'll shift this particular term in this denominator, you will gain that what exactly is the definition of this particular coefficient. And the name of this particular coefficient is called the coefficient of emission, because here the radiation is emitted, that's why it's the radiation emission coefficient of emission. So I hope that you understood that what exactly I have talked about, that this particular equation tells us about the radiation emitted by a small mass element. Here EV is the energy, here J is the coefficient of emission, and rest of the things is the small mass element dt, d mu, and d, this is your solid angle. So it means that energy is dependent on this particular type of quantities. Now let's move our second notation. So let's move to second notation, which is generally our second is, you might have guessed that it is the another formula which is the absorption, related to the absorption of radiation. Okay, so now let me clarify this. So suppose that it's a thick material of thickness ds. This is a material of thickness ds, and radiation entered into this. So let's say, let me draw it one more. Okay, suppose that this is your radiation, this is a radiation, and it enters into this particular element. So what will happen is that when it enters into this particular element, due to different type of the phenomena going inside this, like the scattering, absorption, and all of this, will change the radiation. It means, suppose that the radiation was initially I mu, and after escaping from this particular element, let's say it is I mu plus d I mu. So remember, this d I mu can be negative also, can be negative, and certainly it is negative in our case. It means this radiation intensity decreases when it enters into a volume element, this particular volume element. And why it decreases, I've said about this, is due to the scattering, absorptions, and all of that stuff. So now if the material is getting absorbed, it means some intensity of radiation is being absorbed by this particular element. So now let's see how we are going to define this in the mathematical term. So let's see. So in the mathematical term, it is defined as E subscript EMM. It means emission. 1 minute, no, we are going to discuss about absorption, not emission. Sorry for this. Okay, so we are going to talk about, suppose that d I mu. So this is the change in, this is the small change in radiation, and this d I mu radiation, which is gets lost when entering into the cylindrical or any type of the element, can be defined as negative of your initial radiation I mu k mu rho into ds. So first of all, let me clarify this, that what exactly these terms are. So this is your initial radiation, and this is the small part of radiation which gets absorbed, or you can say that it gets dismissed after when it comes out to the another surface. I mean to say, suppose that there is a cylindrical element like this, and initial radiation IV enters into this particular element. So after this, what will happen is that when it escapes from this particular side, it will become I mu minus d I mu. It means the radiation gets decreased. So how I am going to calculate this particular d I mu? It's a small change in this radiation, and this particular is going to be using this particular formula. So I hope now you understood that what exactly is the significance of these d I mu. Okay, so now let's see. This is your initial radiation. Now discuss about the second term in the equation, which is k mu. So this is the coefficient, just like in the emission we have doing. Here is the emission coefficient, just like this. In our second case, it's the absorption coefficient. This is the coefficient of absorption. So this is the coefficient of absorption, and the next term is this rho. I hope that you know this is density, and ds. So let me clarify what exactly ds is. So ds is generally thickness of your material in which the radiation is going. Suppose that the cylindrical element, so ds is the thickness of this cylindrical element. So now we have discussed about the absorptions and the emission of radiation, how we can calculate that a small amount of radiation which get absorbed when entering into the material by using this particular formula and all that stuff. So I hope that now it clears to all of you that what is how we can define emission and absorptions in the radiation and how to calculate it. So now suppose that I have written the formula. Let me rewrite the particular formula, which is d I mu is equals to negative of I mu rho j mu ds. Suppose that I put this down here. This is your equation number 1. Let's say, and if I do this, it will become d I mu divided by I mu. It is equals to negative rho j v ds. Now what I'm doing is that I'm trying to figuring out the formula which can calculate the decrease in the intensity of the radiation. So now what I'm going to do is that performing the integration. So doing integration, when you will do integration, you know that what is going to be this is going to be ln IV is equals to the integral of rho jv ds negative, and I can generally transform this in the e to the power term, which will I mu is equals to, okay, so I have not written the limits, and I think without limits it will not, okay. So here let's say IV was our initial, and IV dash, let's say, was our calculating what will be the intensity after this. So I mu was initial, and let's say I dash V was our final. So now using this particular rule, what I can say that it is equals to the log of, by using this integral, I dash mu divided by I mu. Here mu is the subscript, and it is equals to the negative of the integral of the rho jv ds. Now after performing this, after removing the logarithm, what I can conclude is that E okay, so by doing this we can do that I dash mu is equals to the I mu, which is our initial, and it is equals to the e to the power negative of integral of the rho j, sorry, this is j, rho j mu ds. So this is how we are going to define this integral, and here ds is the very small thickness, so integrating it from 0 to s. So now this is our very important formula, which will guarantee and which will use to find out that what will happen to the radiation for the different thickness. Here I'm assuming that you know that what exactly this was our initial radiation. So this was our initial radiation, okay. This is our ds thickness or all that stuff. So this is a very particular formula which can help to calculate the radiation emitted when radiation gets absorbed, and after absorbing the radiation, what will the final radiation coming on from the other surface of our element, like in the case of cylinder. So this formula can be used, that what exactly will be the radiation. So if I will try to depict it in the graph, it's like this. Suppose that I made a cylinder, okay. Here it was, let's say, I mu. So if someone asks you that what will be the radiation emitted when it leaves this particular element, so what will the radiation here emit by after escaping from this particular element? So this will be I dash mu, which you can calculate using this particular formula. So I hope that you understood exactly that what exactly this formula tells us. So this is our basic information of all the terms that we are going to use in deriving these equation of transfer. Now this is our basic term. Now I have not discussed about the scattering of radiation. It means the formula that we can use that to derive the equation. So scattering of radiation. So how we are going to define the E scattering of the radiation, because when you will find out that we are going to calculate the equation of transfer for the atmosphere in which there is all three happening. I mean to say that I want a formula that will guarantees us that this particular ES, E scattering, E emission and E absorption. So we are going to derive a general differential equation which contains all these three. So this is the topic of the next video. I'm ending this video here on the scattering of radiation. I will not discuss about the formula because the time is not there. So in the next video, finally I will discuss about the scattering of radiation, what formula is going which we can use to derive the scattering. And finally, in the next video, I'm saying to you that I will derive the differential equation of the equation of transfer, which is not very hard, I'm giving you hint. What you have to do is that you have to, if you want to do it on your own, I will give you a hint that you should know about the formula of the scattering, and after knowing about the formula of the scattering, you can use the energies conservation. It means, like, suppose that E was the final energy and E was the initial energy, and this can be termed as the E due to scattering plus E due to absorption plus E due to and E due to emission. So this is a formula I am giving you. Using this formula you can on your own derive this, but if you can't, I will make a third video on this particular equation. And one more thing I'm going to tell you, that when I'm studying the astrodynamics on the stellar dynamics or more about the thermal equilibrium of these stars, we have to encounter the higher mathematics of the statistical physics, like the Maxwellian distribution, which is a kind of hard topic to derive, but I will try to make a video on the statistical physics also. And recently I have posted a poll in which I've asked about the general relativity section. So yes, I will also try to do the general relativity, but not directly into it. First of all, the mathematics of it, like the tensors and the differential geometry, and I made several videos on that, on which book you should follow to know about the tensors and the differential geometry. So I will put the link in the description box. You can see that the video on that recommendation of tensors and differential geometry. So this is for today's video.